Hi, everybody. I'm Yuji Takubo. I'm a student at Space Rendezvous Lab advised by Professor Simone D'Amico. Today, I would like to talk my research goal presentation titled Safe and Goal-Oriented Spacecraft Trajectory Generation via Learning and Optimization. So I will go over like each part like step by step, starting from like introduction. So distributed space systems, which is a space systems comprised of multiple spacecraft, but not single spacecraft, has been proliferating over the last decades. Applications include like crew docking or on-orbit inspection, like refueling, to debris removal, to science observation, and then so many more. There has been so many legacies already, including like a Grace, Prisma, Tandem X. More recently, Address-J made a successful RPO, rendezvous and proximity operations to upper stage for inspection. And then in Space Rendezvous Lab, we are planning to launch VISORS, which is like a distributed space telescope, which can capture like a unprecedented level of accuracy to capture the solar corona. So although applications like very wide and vast, they are like they have fundamentally sharing the key issue in terms of like a guidance and control, which is they need to be safe, and then they need to be goal oriented, and they need to be optimal. So what do you mean by safe? You need to maintain some sort of like a safety metric over the like horizon, particularly in orbit. For example, one great example is like guarantee of miss distance under the loss of control and uncertainty, which is called passive safety specifically. What goal-oriented means is like they need to be identify some objectives as they approach. Imagine you're going to unknown object in orbit, which is tumbling. You might need to identify the shape of it, and then you figure out, okay, where to dock, how you approach it. So you're changing the objective of like the approach. So that is like very much needed in the future technology. Finally, because we are in space, we cannot generally have unlimited source of energy or fuel. The fuel optimality particularly is like extremely important in the like spacecraft guidance and control community. So I would like to go over a brief overview or more or less history of like how people have been dealing with this problem. One most traditional method is like a closed form solution, which is like very fast and then semi-analytical. So like implementations are very straightforward once derived, but they are mostly case specific, not much scalable unless you specifically tailor for it. And also constraints are very hard to enforce, and it's very hard to be goal oriented in that sense. Another method is like optimization method, or including indirect method specifically. And there are another method also called reachable set theory, which is somewhat in this like realm, which has like a general like very strict optimality condition of like necessary and insufficient condition, specifically using Pontryagin maximum principle or reachable set. However, sometimes they're very sensitive to code state, or constraints are generally hard to include. Another optimization method has been like called direct method, and they're very general and they can pursue local optimality. And the great method, a great part of like this direct method is like you can easily integrate the constraints, which is really nice in terms of like spacecraft guidance and control. However, they sometimes like tend to be very high dimensional due to the nature of like discretization variable, especially in the time direction where you lose like the strict optimality of it. Finally, although there hasn't been deployed yet in space, people have been looking into a lot of like learning-based method, including reinforcement learning or imitation learning. This is mainly like along with the surge of like these method in the robotics community. They can potentially capture the global solution landscape via offline learning or offline training. However, there is like a big caveat when you want to deploy this like learning-based method directly in space, because there's no guarantee of feasibility or optimality in the generated trajectory in general. Also, like they might consume like so much energy like before like deploying it. So like we call it data hungry. And those are some like pros and cons. So specifically, there's like a big interest of using optimization, as I mentioned before, in order to chase optimality. However, like there are some like numerical issues out there. So the idea here people are thinking is like, can we take both advantage of like optimization and learning-based method. So like this leads to this emerging paradigm of like learning-based warm starting. Learning-based warm starting specifically means we train a model so that their output can be used as a warm start or initial guess of a complex trajectory optimization problem. Essentially, we query boundary conditions or performance metrics we want to have, and then we throw that into inference model to give us like a nice initial guess trajectory comprised with like maybe state and then like control. This we then fed as an initial guess of like the following non-convex optimization, which requires initial guess to be filled into the optimal trajectory, which is like locally optimal nearby that solution. However, we expect the inference model have like a global capability of like searching solution. We expect the retrieved initial condition sufficiently close to the global solution, global optimal solution. There have been like a lot of like studies of doing this like type of philosophy. Essentially, we use some data-driven method to initialize the constraint trajectory optimization, including some of them does not include machine learning or learning-based method, but more like a sampling-based manner, such as like the first one, including particle filtering. And there are so many like architecture that has been presented, including like MLPs, diffusion policy, etc. And today, specifically, we would like to focus on autonomous rendezvous transformer that Space Rendezvous has been like working on over the last couple of years using specifically transformer architecture. So although there has been some extensive work, most of like literature has been lacking like two aspects of like the warm starting technology in terms of like the practical deployment of the learning-based method in space. One is like they're missing some like guarantee of fault tolerance or robustness to the uncertainties. As I shown in the figure or illustration, usually spacecraft has like relatively high uncertainty because of like navigation error, uncertainty in dynamics modeling, uncertainty in actuation. So we would like to ensure that some specific constraints are specifically satisfied with a probabilistic margin or buffer. Another aspect of it is like we really don't know if the generated trajectory is like trustworthy or good enough to be as an initial guess. Although like the following optimization has been serving as already a buffer of it, non-convex optimization, for example, sequential convex programming, has a tendency of like failing convergence or even like going to a severely suboptimal point as we throw like a poor initial guess. So we would like to evaluate if the return generated trajectory is somehow trustworthy or like they are going to a good direction in terms of like a global search solution. So over the past years, I have been working on this two problems by integrating one is like chance constraint optimal control problem, it's so called, to be able to handle uncertainty, also like fault tolerance. Another work I have been doing is like introducing post hoc acceptance check to reject potentially bad initial guess trajectories. Potentially bad is a very hand-wavy, but I'll talk in a minute. And these works are summarized and presented in the IEEE Aerospace Conference last March. And then more detailed results are on this paper. So I would like to go into the methodologies. So first of all, I would present what we want to solve at the end of the day, which can be formulated as like a fault tolerance trajectory optimization under uncertainty. This can be modeled, one way to model this, not this is the only way, but is like to formulate a chance constraint optimal control problem, CCOCP. So this can be formulated as a minimizing some sort of objective function under dynamics constraint. And we also assume that state uncertainty model can be explicitly evaluated as a function of like a mean state and then control. And then we can set some sort of probabilistic fault tolerance constraints shown here, where M star is like a general fault tolerance path constraint. And then it needs to be admissible control domain and then satisfy boundary condition. I think it's pretty straightforward. And then here, by assuming several things, such as like Gaussianity of uncertainty, we can decouple this like probabilistic fault tolerance constraint into more like a tractable form like this. In fact, we are allowing like this to be finite dimensional constraint from this like infinite dimensional constraint, which can be formulated as a probabilistic constraint. And now like we are showing here as a deterministic constraint. So Though I will present the workflow of ART first of all. The ART or autonomous rendezvous transformer can be decoupled into two phases. One is like a training and the one is deployment. And training can be done in offline on ground. And then when deployed, like we expect to be performed in orbit. So these are main three items we are going to cover. One is like how we tokenize or how we ensure that neural network can understand this is a trajectory sequence. And then after we define this, we solve a batch of like optimal control problem with some domain randomization. And then finally, with that data set, we train the transformer model. So we feed the boundary conditions, solve a batch of like optimal control problem, make a trajectory data, and we tokenize it, and then we train it. Once it's trained, we then give a specific boundary condition where we are at and where we want to go in like space in orbit, which is like then propagated using transformer, and initial guess is now fed to the CCOCP once again on board. So I would like to go over how transformer generates the trajectory in a little bit more detail. I believe like most of you are already familiar with like how transformer generates like a token, for example, in ChatGPT. But the idea here is like we query the first step of the state, for example, and then we expect the transformer to return like the next step with corresponding control input to that point. And then we bring back this entire trajectory sequence once back, and then transformer predicts once ahead again. And then we keep doing and keep feeding the entire trajectory until like it hits a terminal state or like terminal time. So this is a little bit different from like Markov decision process, but it's called sequence modeling. And they are like some advantages that are confirmed to be better in terms of like learning the entire trajectory history. Although the original optimal control is Markov decision process, which means it should be able to like determine the optimal state given just the current state, if that makes sense. So that's like a small hack we are doing in this like learning context in order to like give a more rich information to the transformer. So as I mentioned, we need to tokenize the trajectory. And how we do it is like we add this like performance parameters P in front of like the states and control X and U, which is like here the performance parameters are defined as like R and then C, two tuples, which represents reward to go and constraints to go. Essentially, it represents how much reward we want to spend or we can like get, or more like in guidance and control word, how much fuel we can use until the end of the trajectory. And then constraint to go similarly indicates like how much constraints we can violate to get to the terminal state. Ideally, we want to be zero, right? And my contribution was like including this like constraint to go, including the chance constraint evaluation into the constraint to go formulation as a binary indicator function. The thing is like, because we are now like showing the infinite dimensional probabilistic constraint into finite dimensional constraint, we can now explicitly embed and evaluate if this indicator function is like satisfied or not. After we tokenize the entire trajectory, then what we do is pretty much straightforward. We just solve a lot of like CCOCP and make a trajectory data set. And then using that data set, we train transformer model to minimize this like loss function, which is characterized as like basically a square of like offset of like transformer's prediction of state and then transformer prediction to the output, transformer's prediction of the control that you should take. So now that was like a training part. We would like to move on to the deployment or like how it's going to actually infer the trajectory. Because in spacecraft, usually we have like onboard dynamics model, which is like somewhat accurate, at least like more than like what neural network thinks inside. We actually use like a small trick called dynamics in the loop procedure, which means ART actually only infer, or we only take the inferred control state, but not the state, which is like internally propagated into neural network to propagate the dynamics to generate the initial guess. By doing this, we can leverage the known like dynamics model on board to generate the dynamically feasible trajectory, which is a huge advantage because like we are now throwing into the non-convex trajectory optimization, which needs to satisfy constraint, and then by default we can satisfy the dynamic constraint. So which is a huge advantage of it. And the important part is like here, as shown in the post hoc acceptance check, and now, like, like as I mentioned earlier, we would like to evaluate if the generated trajectory is like a good or not. So we would like to have some metric of like how close the performance of the generated trajectory is close from what we desired originally when we queried at the very beginning as an input. So we define like some metric as shown here, two metrics of like essentially showing the proximity of like the reward and then constraint. That is like we compared to what we query, so that we can basically filter out some like trajectory which has a large deviation in these two metrics. Essentially indicating like how far the reward and then the constraint are offsetting from like what we originally want, if that makes sense. So now this is applied to the low Earth orbit fault tolerant rendezvous trajectory optimization. The objective function is defined as a field optimality, and we only consider impulsive control. The time window for this rendezvous is like 2 hours. In the relative dynamics model, we use quasi-non-singular relative orbital elements with J2 perturbation and arbitrarily eccentricity. And chief spacecraft is like supposed to be around near circular orbit, 400-kilometer altitude, which is kind of mimicking the International Space Station's geometry. By the way, I'm only considering that dual spacecraft system, where we are assuming one spacecraft is trying to approach to the International Space Station, which is chief. As I mentioned, we need to consider like we would like to consider uncertainties. So we are providing uncertainty models here, which is navigation uncertainty using some values from Artemis, which is a Space Rendezvous Labs angles only navigation toolkit, and also actuation uncertainty, and then a model as acceleration within the dynamics. So the duality of like uncertainty, there exists a contingency that we also want to address, which is the part of the fault tolerance. We specifically define a passive safety constraint, which ensures that the trajectory is always outside of like a domain called keep out zone or approach ellipsoid, not only during the controlled sequence, but also like the drift trajectory. Essentially, we would like to ensure that enough separation is ensured even after the event of loss of control at every single control node possible, with some probabilistic margin that I mentioned uncertainty model. So like this like fault tolerance probabilistic constraint is actually very much a big constraint that we need to evaluate, which is of course non-convex. And by embedding this like constraint, we generated a large number of trajectory, which comprises like 115 trajectories as shown here. The top one is like a deterministic trajectories, which only uses like a deterministic form of passive safety. So we nulled all the uncertainty sources and then solve it. And the latter one is a chance constraint trajectories, which now we toggled on all the uncertainties existing and ensure they have a 99% of like chance, which is like still outside of like keep out zone, even after including those uncertainties. So you see a little bit, the solutions for trajectories diversity a little bit more in like the deterministic case compared to the chance constraint case, which shows like the solution space like to some extent smaller. So again, but I would like to present some like intuitive understanding of like what is art actually enabling. So this is like some case where I pulled out from like the generated trajectory, where like the convex trajectory, like the simple convex optimization algorithm, which only satisfies the boundary condition and the dynamics constraint, ends up in delta V of like 4.8 meters, which is shown in the black trajectory. When you feed this as initial guess into the sequential convex programming, it converges to a point where delta V is like 5.3 meters, and then like it's somewhat similar to the like original black trajectory, which is shown in blue. Although it's like looks pretty similar, it actually adds up a lot of like delta V to be passively safe. However, when you like query the same boundary condition to art, it results in the orange trajectory as we show, which is completely different from the convex initialization. And it lands to like a delta V of like 4.79 meters, which is actually below the convex initialization, because it does not satisfy some constraint such as boundary, like terminal constraint in this case. However, after throwing this as an initial guess to the sequential convex programming, it lands to some like another trajectory, which is red, which satisfies the passive safety, and also the objective function is exactly the same to the lower bound, to the like digit of like the third decimal point. So like noting that convex solution is like the possible lower bound because it's a relaxed form of an optimization, you can see some like effects of like art enabling the global search of the solution space and generating the initial guess that is very close to the feasible set, if that makes sense. So I performed two statistical experiments. One is like the comparison of like chance constraint optimal control problem and deterministic optimal control problem. And the second one is like I'm doing some statistical analysis on like if the introduced post hoc acceptance check is actually working. So we did a lot of like statistical analysis over like both like basically comparing like if the converged solution of sequential convex programming using the convex initialization and art initialization, and then the performance metrics can be wide if it's more optimal, like, or if it's less infeasible, statistically speaking, or at the end, if it converged faster or not. And these some like statistical methods are shown here, statistical properties are shown here, where particularly, for example, infeasibility rate, comparing some like blue bars and then like orange bars, you see like the converged solution using like art initialization has like significantly less infeasibility rate. And similar trend in like optimality is also observed where the art initialization actually contributes to reducing the terminal optimal objective, as well as the total runtime. So although like we are including the inference time of the transformer, which inevitably adds sort of like additional computation time on top of the sequential convex optimization, overall we observed that like it leads to less iteration to convergent SCP, thereby reducing the total runtime. So which is really desirable. Next, we'd like to go on the post hoc acceptance check. As I introduced here, there's like a two metrics. And then what we did is like we basically provide some like calibration data set, and then we observed some like trend of like like how the distribution of like art locates. And then by purely seeing this like two metrics, which can be obtained before we do sequential convex programming, we basically heuristically set up like some like criteria. You see some like lower bound and upper bound, which is around 0. Essentially, 0 means like your like resulted art generated trajectory satisfies like exact on the reward and constraint that you want to satisfy. And then we essentially saying like we set a bound and an interval. And if you're like somewhere in this margin, we take as like a valid initial guess. Otherwise, we reject this art solution. And instead, as a fallback solution, we took CBX convex solution as an initial guess. So the results is like shown here. This is a little bit hard to read, but essentially showing on the x-axis the degree of like difference in the converged solution compared to the art initialization and then convex initialization. What this is showing is essentially on the right side, art warm star actually contributes to reducing the optimality or increasing the optimality by reducing the objective cost, as I showed in the like couple of slides ago. But statistically speaking, there are also like solutions which is on the left side, which means if you do convex initialization, that actually ends up in better optimality compared to the art initialization. So they basically like art is like not doing a good job. However, by simply taking this like post acceptance criteria, if you can see like the bars, like red and green bars, like shown here, which is like the maximum and then like the minimum values like in the population, you see like the left side of like distribute population essentially collapse to like very close to 0, which indicates the CBX warm start, or essentially there's almost no solution that underperforms CBX initialization, which is really a good sign, especially considering there are some still population remaining on the right side. So essentially, by introducing post hoc acceptance criteria, we are somewhat keeping the nicely performing art initial guess, while rejecting most of the art initial guess that performs like really poorly. So again, like I would like to visit the conclusion. The original motivation was fusing learning-based method and optimization method for safe and a goal-oriented guidance and control for distributed space systems. And then the past work I have been doing is like on top of the architecture of autonomous rendezvous transformers, or ART, I embedded like chance constraint optimal control problem and post hoc acceptance check to ensure some robustness in the generated trajectory, as well as the fundamental optimal control problem itself as well. So to wrap up, I would like to briefly cover like what I'm planning as a future work, and then through my PhD. I'm thinking of like three main topics like that I can think of right now. One is like a runtime monitoring. So I introduced like a very heuristic post hoc acceptance check, and it seems to be it's working, but we'd like to more formalize this method to ensure some statistical guarantee of like learning-based method actually showing like nice property. And this is very much related to out of distribution detection or fault detection of like a machine learning method. And there are multiple things you can do, including conformal prediction, which statistically validates the black box like trajectory predictor in the like formal way. Or you can also think of like some out of distribution detection by looking into the latent space by checking how transformer perceive the current state, if that makes sense, comparing to some successful like trajectory generation. And another part like I'm looking into is like a hardware testing. I showed that the GPU's inference even included runtime is like smaller. However, the current like space graded GPU is significantly like poorer in terms of performance. So we are actually expecting some sort of like increase of computational burden, which is probably intractable at this point of stage. So the interesting potential motivation of the research is like the distillation, where you can now like using this like Oracle model, you can transfer the knowledge to a smaller model by retraining that part. And then there is of course a trade-off of computational burden or size of the model to the inference capability. So looking into those trade-offs would be pretty interesting idea of research. Finally, integration of like vision or more multimodal sensor information is would potentially open a new capability of like a spacecraft autonomy, in my opinion. Because transformer can like very naturally intake multimodal input, as you may know, in the form of vision transformer or like so on. There's nobody stopping us from like actually directly feeding, for example, spacecraft image or other sensor information into ART to generate a trajectory. What we are doing is like only the top part, not even the left half side of like the top part, but given the state and then covariance, can you generate a trajectory? But by slowly enlarging this like input state, we are hoping that spacecraft can more generally capture what is going on that is like potentially not be covered within the like traditional optimal control problem. One of like the interesting problem is like, for example, if you're in the like on-orbit inspection and then want to do some like circumnavigation around unknown tumbling object, you don't know the shape as well, then how can you maneuver to a specific point which you don't know to minimize the uncertainty of the shape? And after that, how can you move on so that you can actually approach and then dock or capture some like tumbling object? That is like using like the current methodology, the state of the art really cannot capture it and address it. And I'm hoping like these type of advancement actually enhance those type of like safe, goal-oriented, and optimal spacecraft guidance and control. So this is a publication list. I have like 4 publications like thus far. I'm more than happy to talk other stuff as well and reference. And thank you so much.